All right. Let's get started with midterm review. So I did grade your homeworks and quizzes, and one of the topics that people asked if I would go over was more distributed load stuff when it comes to shear and moment diagrams and the equations. And from grading your homework, I see why. So how should I explain this? Well, let's do an example. Okay, we've got a beam, and let's say it's got a distributed load in the middle here. And this distributed load, let's say it's 3 kip per foot. And I've got a thing for 3 today. Okay? So pretty simple beam. What's the magnitude of this load? The total magnitude? 9 kip, right? 3 times 3 would give us one big load here that's 9 kip, which would then tell us we've got 4.5 and 4.5. Okay. So graphically, what we did on Wednesday is we could say, oh, 4.5, that means I jump up 4.5. Nothing happens till I get over here. Then I have a constant negative slope. Okay, sorry, this should be a horizontal line. It looks like it's not quite horizontal. And then nothing happens, and then I jump back up. Okay? Right? Where this is 4.5, and this would be negative 4.5. And then I can do the same thing for moment. But now I look at the moment and I say, okay, I have a constant positive slope of 4.5. So it's going to look something like this. Sorry, it'll go out to constant slope, so straight line. It's right here. The change would be 4.5 times 3. 13.5. Is that right? So we're at 13.5. Okay. Then we have tangent, but decreasingly positive to a flat spot right here. So now we've got a curve going on. And then it's going to do that same curve down. And then it's going to straight line down, right? So it's kind of like a mound where we have straight lines and then a curved top or a hill. So how do we find the magnitude of that point right there? How would we find the peak of my little mound? So we could go back and solve. We can actually do it graphically here too, though. How could we graphically do this? I'm at 13.5 here, right? And remember, the change in the moment diagram is equal to the area underneath the shear diagram. So if I could find the area of this little triangle here, which I think is 4.5 by 1.5 divided by 2, right? It has a height of 4.5. This length is 1.5. So 4.5 times 1.5 divided by 2, 3.375. That's the change as I go from 3 meters to 4.5 meters in the middle. You said it's 3.375. 3.375. So that'd make this 16.875. Okay? And we have our shear and moment diagrams. All right? But in the homework, I asked you to do it not only by doing the shear and moment diagrams, but by finding the values. And here's where people messed up. They messed up when they were cutting through a distributed load. So let's say that we're going to cut this right here. Okay, we're going to cut it right in the middle because we decided we forgot how to do this graphically. So we need to draw a free body diagram. Okay. And then we'll draw our shear and our moment. And we remember that our cut is x distance away from the end. Okay? So then I can, and it's how we treat this cut distributed load where people often struggle. Okay? So how much of this distributed load do we put in here? Well, we need to figure out, remember that this is 3, right? And we like to simplify this and say that it's one, resultant force in the middle for our calculations. And the magnitude of this resultant force that I simplify the distributed load into is the magnitude of the load distribution times its length, right? So in this case, the magnitude of this force is going to be 3 kip per foot times whatever this length is. How do we get that length in terms of x? Exactly. We need to figure out that this is x minus 3. Right? Because this is the whole length, and we take this away, that would leave us that little piece, x minus 3.
If you cut it down the middle, wouldn't it be x take away 1.5?
Sure. But right now, if we just want to write the equation for this region, this is how we'd have to do that. Okay? So now we can say sum the forces in the y direction and set them equal to 0. So what's happening in the y? It looks like I have 4.5 up minus v minus whatever this is, which it looks like it's 3x minus 9. Right? I'm just distributing this out. 3x minus 9 equals 0. So we could say that v is equal to minus 3x plus 13.5. Okay. Does this fit with our graph here? Remember, I take x not just for the region, but x is all the way from the end. So at x equals 4.5, this would be negative 13.5 plus 13.5, which gives us 0. So far we look okay. Now, I think where people get into the most trouble is when we come back and we say, okay, let's sum the moments about the cut. We always sum them about the cut. Okay. So if I'm summing this about the cut, I'd have minus 4.5x, right? That's this guy. Plus, what am I going to do with this? Well, I'm going to use the magnitude of that force, which we think is 3x minus 9. That's the magnitude of the force, times the distance from the cut. Oh, man. What's that distance from the cut? Hmm? No, because I'm summing my moments about this point here. So I need to figure out what this distance here is. Right? We know that the whole distance of the distributed load is x minus 3.
X minus 4.5.
Nope. Okay. So if I know that this distance here is x minus 3, and this is half of that, wouldn't it just be x minus 3 divided by 2? Right? Plus m equals 0. This looks kind of ugly, huh? Right? But so what I just want to drive home here is when you have a distributed load and you're cutting in that region, you need to make sure that you put the resultant. I find it best to write the magnitude of the resultant above it. And then you need to remember that that resultant doesn't happen right at the cut. It happens in the middle of the distributed load. Okay? So what would this be? This would be m is equal to 4.5x minus 3x minus 9 times x minus 3 times 1/2. Gosh. This is like, gosh. 4.5x, let's see, we'd have minus 1/2 3x squared minus 9x minus 9x plus 27. M is equal to 4.5x minus 3/2 x squared plus 9x. That's plus 27, right? It's plus 27 minus 13.5. Yuck! Excuse me? Yeah, I could still simplify. Simplifying Nazis. Minus 3/2 x squared plus 13.5x minus 13.5. All right? Gross.
Would that still work for the part of the section that's before the distributed load? Like, would you have a negative in that? Or like
Would this work for the section before the distributed load?
well, the section includes the part before distributed load that you made at the top.
So this works so there's 3 regions in this problem, right? There's 1 here, 2 here, and 3 here. And so these equations are good for region 2, right? Yeah. Yeah. Okay? So, let's give you a... Say that again?
Why'd you split region 2 like to the middle of it and not to the end?
Oh, it doesn't really matter where I split region 2.
Just as long as you cut some.
As long as you cut someplace in the region, right? Because my cut is at x. So I just happen to have drawn it that's halfway through the region, but it could be right at the very, it could be at 3.1 meters or it could be at 5.99 meters. Both are still in the region and valid for x. Okay? Or feet in this case, I guess. All right, so let's have you work one of these. I want to make sure you got this. Okay, go ahead and find the shear and moment diagrams for this. Okay, and I want you to write up the equations for them. Okay, so you can try it graphically if you want, and then do it equationally.
I don't have an answer for that. Is there something else I can help with?
No, thank you, not right now.
You're welcome.
Yeah. Yeah. That's nice.
Shows up audibly in the video.
That was like a perfect time, honestly.
Everyone got this problem? I'm going to pause it and give you 10 minutes to work on this, then we'll come back. All right. What'd you find the reactions to be?
Negative is negative 62.5. V is 312.5. Thanks, man. That was really insane of you. You're welcome. I'll let you read.
Oh, it's frozen. There we go. Sorry. Negative 62.5, so that means we've got this guy's going down, 62.5. This guy's going up, 312.5. So from here, what did you do? Did you do it graphically or did you go equations? Okay, so if we start graphically, looks like we jump down 62.5. Nothing changes till we get over here, and we jump up 312.5, which would be 250. And then we have a downward negative slope of 50 per foot for the next 5 feet to get us back to 0. Not so bad. Oh man, we have a constant negative slope, right, of 62.5 times 10. So we're going to end up at negative 625, right? When we get over here, constantly negative slope, bloop. Then we have a very positive but decreasingly positive, so it's concave down like that, right? So on an exam, you could just do this probably, right? I wouldn't necessarily ask for anything more than this, as long as you can know what this point is, which it looks like it's negative 625. We now know the maximum shear and the maximum bending moment. Does this match with what you guys got? Okay. So what if we were going to break it into regions? How many regions do we have? 2, right? We have 1 here, 2 there. First region is pretty simple. So we can just look at that and say, hey, V has to be equal to negative 62.5, right? The moment has to be equal to negative 62.5x. Why can't I just look at it and say that?
No other force that you have to worry about.
Yeah, there's no other force in that, so if this is x going across, I know as I sum my moments about here, the only thing that's going to have a moment is 62.5x. And it's in the same direction as the moment, so we know the moment has to be opposite of it. So negative 62.5x. Okay? Now let's go to the second area. Okay. Now I have to do some maths. Right? So let's sum the forces in the y direction. Hopefully your equation looks something like that. What does this simplify to, Brendan? Oh, so you didn't do the problem.
Well, I didn't do that, I just graphed it.
And I wanted you to do both, graph it and equations.
You said either or.
No, I said both. Yeah,
You did say both?
I did say both.
Oh.
No wonder you were done. I was like, you shouldn't be done yet.
750
You got 750 minus 50x equals v? All right. I can believe that. Thank you, Liana, for listening to instructions.
Yeah, I gave up on the simplifying the next equation now.
Yeah, okay. So now we have to sum the moments about the cut. Counterclockwise is positive. 62.5 times x minus 312.5 times x minus 10. Right? Yeah. Plus 50 times x minus 10 times x minus 10 over 2. Again, where's this coming from? It's coming from the fact that this is 50 times x minus 10, right? And then this distance here is x minus 10 divided by 2, right? And then we'll have plus our moment and equals 0. Okay, and you can solve this if you want, and you'll end up with the equation for this curve here. Okay?
Are you not going to simplify it either?
Yeah.
Don't plan on it.
I don't blame you.
Yep. I'm not going to simplify it. Okay? So what are some tricks when you're working problems with distributed loads that you need to remember?
Square distributed loads are divided by 2 for distance.
Square distributed loads are divided by 2 for distance. It's going to be a curve. Okay.
Parabola.
Use the area between, like, how far down it goes.
Okay, use the area. You just have to be really careful that even if we slice it mid-load like we've done here, that means that there's a new resultant force that's going to be someplace where in the distributed load. Let's do one more that's a triangle. Okay?
If it's a triangle in the middle, then you will already do the equations, so.
Yes, probably. There's a few. So the question is, if there's a triangle, is it better to just do the equations or do it graphically? I mean, to be safe, you can just always do the equations, but there are some times where you can still get away with doing it graphically. Okay. So let's do. Let's do one of these. We haven't done one of these in so long. This is an awning outside of a building. It's cantilevered, and it has a bunch of snow on it. Triangular snow. Okay. And we'll say that this is 50 pounds per foot up here. And let's say that the beam is 8 feet long. Okay. All right. So let's start with the shear. Well, we know that this has 50 pounds per foot and it's 8 feet long. So 50 times 8 is 400. Divide that by 2. We're going to get 200 as the resultant. Right? 50 times 8 is 400. Divided by 2 gives me 200. I'm just finding the area underneath the load curve. So that means that right here we must have a resultant of 200 acting up. So we can jump up 200. Then we have a constant negative slope of 50. And our shear diagram looks a whole lot like our distributed load diagram. Right? What will our bending moment diagram look like? A curve? How does it start, though? Does it start at 0 here? What's the result? I don't know, does it? Someone is a little snippy today. What moment has to be here in order for this thing to be in static equilibrium? The resultant, right, we're used to. So far, I've just been giving you beams that are simply supported instead of cantilevered. But in a cantilevered beam, we're going to have some, we have just the result, or a reaction force in the vertical, and then we have a moment reaction, right? And the moment reaction here has to counteract the moment of the load. So it looks like if we were to, just to find our reaction, sum the moments, well, let's call this A, about A, and set that equal to 0, counterclockwise being positive, we'd have the resultant, 200, acting in the negative direction. Where would it act? 1/3, so 8/3 over. And then I'd have plus M equals 0. So it looks like there is, to start with, a moment of 200 times 8 divided by 3. 533? Yeah, it is. 533 pound feet. Okay, so that's right here. 533 pound feet. Positive or negative? Positive in this direction. Okay. So in our graphical approach, I don't think I ever talked about this. When you have a couple moment that acts on this, it causes a jump in the graph. Just like a point load causes a jump in shear, a couple moment causes a jump in the moment diagram. And the rule is a clockwise moment causes a upward jump. And a counterclockwise causes a downward jump. Okay? In the graph. Yep. So we just found that right here there is a counterclockwise 533 pound-foot jump. Goes down. And this should make us feel good because if we look at this, we have a positive change in the moment as we go from 0 to 8, right? Because everything in the shear is above the abscissa, so that means we have a positive change in moment. So that what this is telling us is we're going to start with a very steep slope, 200. We're going to go to 0. And there's our moment diagram. Oh, it's a parabola, I think, but okay. And it starts down here at 533. Okay. Let's do one more. Because this one didn't make you slice anywhere in the triangle, and I want to make sure you understand how to slice in a triangle. Did you hear that? I want to make sure you understand how to slice in a triangle. In a triangular distributed load, I want to make sure you know how to slice it. I'm going to make sure you know how to slice a triangular distributed load by Monday. Should I say it one more time? All right. Oh, this is going to be a great one. Yeah, it's going to be awesome. And right in the middle, snap.
And is the other one also 100 pound-feet?
Yep, they're both 100 pound-feet. It's symmetric. How wide is this bad boy? Let's say it's 10 feet. The whole enchilada. It's a 10-foot enchilada. Oh, it sounds glorious. Okay.
A lot of work to make.
Yeah, you'd have to have a big oven for a 10-foot enchilada. I'd say an approximately a 10-foot long oven.
Is this your next passion project?
No, I'm not going to be building a 10-foot enchilada oven. I think if I had to build a 10-foot long enchilada oven, I would just get a piece of like 6-inch pipe. It was 10 foot long, and then you would just then I'd get a piece of 5-inch pipe that you could that would be the pan for your enchilada, and you would just slide it in there, and then you just have a broiler strip that went along the top of it. You could totally build a 10-foot long enchilada oven. I know what I'm doing this weekend. Okay. All right, how many regions do we have? Or do we want to just start graphically? We want to live wild and crazy? Maybe we should solve for the reactions. Solve for the reactions first. So if it's 10 foot long, the area underneath this triangle would be 5 times 100 divided by 2. $500 divided by 2, I think that's 250, right? So what we're really going to have is 250 here and 250 there. But what's this 500 pound-foot thing do to us? Oh man, we're going to actually have to solve for reactions for reals, okay? So let's call this A and B. Sum the forces in the y direction. We'll have AY plus BY minus 500 equals 0. Now we'll sum the moments, not about the cut, we'll sum the moments about A and set those equal to 0. So I have minus 250 times 5/3, right? Because I'm looking for this distance here. We know is 1/3 of 5. Right, going back to grade school when we had to solve problems and we had to look at what the words meant. Of means multiply. 1/3 of 5. I know. That's why I'm here for you, Brandon. Yep. Okay. All right. So negative 250 times 5/3. Plus 500 foot-pounds, it looks like, or pound-feet. Do I need to say times 5 feet here? No, because it's a couple, right? Doesn't matter if, for my moment equation, it wouldn't matter whether this was applied here, or there, or over here. It doesn't matter. Does it matter when I look at my regions or I do my plot? You bet it matters. Okay, so as far as finding the reactions, the external loads to keep this in equilibrium, the location of this is unimportant. As far as determining the internal loads in the beam, the location of this matters. Okay? What else do I have then? Negative 250, blah, 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 blah. Another negative 250. That's this guy over here. What would his lever arm be? Five feet plus 5 times 2/3. Right? And then I'll have plus by times 10 equals 0. Okay? Could somebody with a calculator tell me what by is equal to? Or Brendan with your magic brain? It's 383? 300? by is 300? Anyone else get 300 pounds for by? Gosh, I don't think by is 300. Huh? I think you got those backwards, maybe. Or something. Something's not right. Because if we think about it, AY should be greater than BY. Because it's pushing down on it. You got 200 for BY? Yeah. That I can believe. Okay, so 200 and 300. 200. No, sorry, 300 there. 200 here. Okay, so let's go ahead and for shear, we know we jump up 300. Cool. It is not. Okay. So I'm at 300. I have a negative, or what do I have? I have a negative slope that's decreasingly negative, right? So that means I have a concave up curve because my slope starts negative, and by this point over here, it's going to be flat. But how much is my change? 250. So I'm going to end up at 50. And I think I'm going to do something like that. Okay? Right? Because this is a downward, so it's negative slope. Okay? Now what happens? It's going to go back up? Is it? So think about the magnitude of the slope. This is a very negative slope. This is decreasingly negative, right? So this is very negative, decreasingly negative. If you think about the slope. Okay. All right, so from here, am I going back up? I'm continuing down, right? I'm just switching concavity because now I have a zero slope, increasingly negative. What's my change going to be? It's going to be 250. And then I pop up 200. Whew! Hot dang. That is one funky looking shear and moment diagram. Got it? All right.
So why did the last one look like just a triangle and shape?
Yeah, why did that one look straight, this one curved?
That's a good question. Let's go back to the last one. Because I'm an idiot.
Because I thought it was,
What did I do wrong here?
Should be curvy.
Should be curvy, right?
If it would have been a straight, like, distributed load, then that would have been right.
So I looked at this and said, my slope is negative and decreasingly, right? My slope is very negative and decreasingly negative, and then I drew a straight line. That's not right at all, is it? Whew. Thank you for calling me on my egregious error here.
Because don't you just look at the distributed load, take the integral of that?
So this is going to be, let's think about this one. Negative, decreasingly negative. Concave up, like that. Right? Is this one still right?
No. That number would have been
This number's right. And this actually is right. It's just a higher order. Right? Because I still have positive, decreasingly positive slope. Right? So this one, since I didn't put any equation on this, yeah, it's still right. It's a curve and it's concave down. Okay? But, yeah. So just make sure everyone's on the same page. I screwed up when I drew a straight line here. You need to look at this and say, this tells me the slope. So my slope here, I drew a constant negative slope. That is not true, right? This is a increasing or a decreasingly negative slope. So it starts at 200 with a steep negative slope that goes to 0. So it's a concave up curve, right? I'll do it in a different color. So this is what it should be, like that. This is the actual one, okay? Thank you for catching me on that. It's embarrassing. Coming back to here. Anybody want to do the moment diagram? We can guess, right? What do we know is going to happen in this guy? It's going to be a cubic. But if we just think about it, what's the shear diagram tell me about the moment diagram? Well, just generically, what does the shear diagram tell me about the moment diagram? No, I mean generically. Like don't pay attention to these two. If I have a shear diagram, what does it tell me about my moment diagram? It tells me the slope. So the value of the shear diagram tells me the slope of the moment diagram. The area underneath the shear diagram tells me what, Liana? The area underneath it tells me the change, right? Nope. So the value tells me the slope. The area underneath it tells me the change. Okay? So what that means is that if I could figure out this area that's above, I know, well, let's start with slope. We'll start with the easy one. Okay, what do I know about the slope at 0? It's 300. It's positive, and it's big time positive. Okay, so we know I start big time positive, And then what happens? Do I get more positive or less positive? Less positive, right? So I'm going to get less and less positive. What is it over here? 0. So I know I'm going to hit a flat spot right there. Okay? Then what happens after that flat spot? Negative and increasingly negative. Okay? What happens at this point in my graph? I jump down, right? Because this causes a jump down. So we know that our graph is going to look something about like this. Jump down. I think that's what our graph's going to look like. Okay. Do I know any of these points? Nope. Sure don't. Not a clue. Okay. So how about this? Do I know whether this point is higher than this point? Do I know if this point is higher than this point? Nope, not really. I'm going to have to do a whole lot of work. Do I know where this point is? No. Do I know where this point is? No. Okay. We're going to have to do some equations, guys. Okay. If they're really hard like this, yeah, just start with the equations. But it's kind of fun. We can validate our equations by making a guess. Okay? How many regions do I have? 2. The moment's right on the border, right? So if the moment was not right in the valley, yeah, then we'd have 3. But since it's right in the middle, no problem. Okay? All right, so let's look at region 1. Does anyone feel like swearing right now? You just think it's annoying. Okay. This is going to be hard. Okay. So let's just start with summing the forces in the y.
Why didn't you just split it right in the middle so that you could use the full triangle and not trapezoid?
Or that's supposed to be. Because he likes to,
Because so the question is, why didn't I just split it right in the middle so that I could use the whole triangle and make my life easier? I could if I was just looking for what's going on right at the middle, but I'm not. I'm looking for the equation that's good from A to the middle, right? So I have to write an equation that works if I slice it here or there or there or there.
can't you find that if you slice it?
Yeah, wouldn't it still apply? Because that whole area is X.
No, that would not. That would not work. Let me show you why. Because is this a triangle? So the question is, wouldn't it still work if I sliced it here to write the equation? No, because you're gonna. I'm guessing what you want to do is say, well, it's an equation, so it's just this is always 1/3, 2/3, right? But if my slice is anywhere else, anywhere besides right here, is it 1/3, 2/3? It's not. I have a trapezoid that I have to deal with. Now do you feel like swearing? Okay. Yeah. How do we figure out what this looks like? You're engineers. Do we see trapezoids ever? Nope. What do they look like?
Squares and triangles.
Squares and triangles. Absolutely right.
Good method.
Look at that. There is a square with a triangle stacked on top of it. But,
You don't know the height.
oh, no, you don't know the height. Right? We're going to have to figure this out. This is going to be tough, guys. What's the slope of this line of the distributed load? It starts at 100, and over 5 feet, it goes to 0. So exactly, this is negative 20 pound-feet. Pound-feet, feet, I guess. Right? All right. So sum of the forces in the y. Well, I'm going to have 300 going up. Minus what? We need to figure out what the height of this guy is. Okay, yeah, minus v, sure. Low-hanging fruit there. What else do we have minus? We have two resultants here, right? We have one resultant for the rectangle that's going to be smack dab in the middle. We have another resultant for the triangle that's at 1/3, 2/3. Okay? In order to figure out the magnitude of the rectangular resultant, we need to know what this point is. Okay? The bummer is that that point changes with x. Right? Everyone see that changes with x? Hmm? We do know that the slope is negative 20. Okay. So I'm pretty sure that if this is 100, right? Then this right here is going to be 100 minus 20x. Right? You okay with that? This would be 100 minus 20x. So then the magnitude of this area here is going to be 100 minus 20x. That's its height. What's its length? Times x. Right? Well, I'm just doing shear right now, so it's I don't need a lever arm for it yet. It's this hard just for shear. Wait till we get to moments. Okay. Okay. So this is the height, and this is the length of of the rectangular distributed load. Right? Is that a question, Jason?
How did you get 100 minus 20x?
How did I get 100 minus 20x?
Yeah.
Let me draw it bigger. Okay? So what we're looking at is a trapezoid. we know that this line has a slope of negative 20x, right? And we know that this distance is x. So we're going to divide this into two regions. Okay? This region here would have a resultant right smack in the middle. Okay? The magnitude of this resultant, I'll call it the force resultant, is going to be the height times the length of that rectangle. Right? The length is easy. We know that's x. Right? Right here it's labeled, it's x. The height is the tricky one. We know that over here we have 100, but this has a slope of negative 20x. So I'm trying to find this guy here, which I posit to you would be 100 minus 20x. So if I've gone over 1 foot, this would be 80. If I've gone over 2 feet, this would be 60. 3 feet, 40, 4 feet, 20, 5 feet, 0. Does that make sense? Okay, so then I need to put that back up in here for my height. 100 minus 20x. Okay, that's just giving me the magnitude of my resultant. Now, I need to do the same thing for this triangle right here, where you could agree with me that it'd be 1/2 the base times the height, right? Well, the base is the easy part again. 1/2 the base is x. What's the height? Oh, man. It would be 100 minus the height of the rectangle. So it's going to be 100 minus 100 minus 20x. Right? Again, this is the height of the rectangle. This is the total height. And I'm looking for this height right here, which would be the total minus this guy, or 100 minus 100 minus 20x. So what's that give me? The resultant, 1/2 x. 100 minus 100, I'm pretty sure is 0, right? Minus a negative 20x would be plus 20x. So it looks like this force resultant is equal to 10x squared. Okay. So let's finish our summation in the y. I'm just taking this and I'm moving it down. I'll have 300 minus v minus 100x plus 20x squared. That's this term here. Minus 10x squared equals 0. So it looks like v will equal 10x squared minus 100x plus 300. This jives with our guess up here, right? Because at x equals 0, the shear is 300, which is what we want, okay? All right, it's concave up, which that's right, because the x squared is positive, okay? So far we're doing okay. Now, Do we really want to cook our noodles in the last 5 minutes of class? Let's try and do the moments about the cut. Okay? What is this distance here? What's the distance for the lever arm of the rectangular resultant? That'd be x over 2. Okay? How about for this guy?
1/3, so from the cut, or which side?
The cut's always over, or the cut's on the right. Yep, so the distance from here to here is going to be 2/3 x, right? So this actually isn't as bad as we could have feared, right? Something about the cut, I'm going to say counterclockwise is positive. So I'll have negative 300 x plus 10x squared times x over 3. So to be clear, this is the force resultant for the triangle. This is the lever arm. Plus the force resultant for the rectangle. My head hurts. Why don't I just take the integral of the shear? That would just tell me the change. It wouldn't tell me where it is.
But that would give you the equation of the moment.
So that you could.
You take the shear equation and you take the integral, that'll give you the equation of the moment.
That only gives you the change. That only gives you the change, right? Right? Because so the question is, why don't I just take the integral of this equation to get this? That would happen to work in this case, but it doesn't always work, because what the law says is that the change in moment is equal to the integral of the shear diagram. So if I did that, it's only telling me the change. So it's assuming that I'm starting at 0, right? So it would work in this case, but it wouldn't work in all cases, is why you don't do that.
Can't you just use the fundamental equation of calculus to get rid of that?
So the question is, can't you just use the fundamental theorem of calculus to get rid of that? My answer is, I have no idea what the fundamental theorem of calculus says.
So you got the limits, so you go from, instead of going from 0 to 5, you go from 5 to 10.
Yeah, you just
So it'd be
plug
for
in your
that
bounds.
section would give you the,
So when you're
So we
evaluating,
do like
you put in the bounds that you want.
minus 10 or x minus 5. Yeah,
Because it's still the same equation.
Or x.
No, because this is still just, I believe this is still just telling you the change. So that would work in the first half, it wouldn't necessarily work in the second half.
Well, you change your bounds.
I'll let you do the second half and see if it works. I'm going to barely get the first half in, okay? So what's the resultant force for the rectangle? It looks like it is 100 minus 20x times x, right? I'm just taking this value right up here and putting it in. What's its lever arm? It's x over 2. Plus the moment at the cut equals 0. Yes, I did go to Stanford, and I do not remember the fundamental theorem of calculus. I have no problem with that. Okay? Is this hard? Yes, this is wicked hard. Okay? I will not give you one this hard. I will give you one with a triangular load, though. So more along the lines of this.
Okay,
Okay?
that's
All right?
do you want us
It's likely, here, let me go a step further. It's likely that it will look something okay? So you still need to be able to do that. You're still going to have to write the equation. If you can do this one, you'll be able to solve whatever I give you on the exam.
It'll be a triangle for the whole. It won't be a trapezoid.
It will be. So I'm saying I'm going to give you a triangle that's not covering the whole thing. So you're going to have to figure out how to deal with that.
Can I ask
Okay.
for graphing it?
Yeah.
Do you want us to use the equations to graph, or are you okay with us kind of just guesstimating what it's going to look
Yeah, so the question is, do you have to graph it following the equations, or are you okay guesstimating? And what I'm looking for in graphs is concavity. Is it concave the right way? Is it on the right side of the axes? Is it positive or negative? And are the critical points labeled, right? So like if I have a graph, maybe I have a moment graph that does something like that, right? I don't care that these are exactly correct. I care that they're both concave down and that you know what the value is at that point. Okay? And even I'll go so far as I don't care. I won't ask you on the exam if you have something that does that. I won't ask you to find that point, right? But I will expect that in your graph of the shear, there's a flat spot that corresponds to that. Right? Or vice versa. Okay? All right? So I didn't get time to get to a 3D example, 3D equilibrium. No, it'll be on the test. 3D rigid body equilibrium. Yeah.
I thought you 3D moment. Like this.
Oh yeah, no 3D shear moment diagrams.
Okay, yeah, I was like,
Not gonna do
hold
it.
on.
I mean 3D rigid body equilibrium. So that's
We didn't get to review. Okay.
yeah.
So is
that-
on what chapters? All of them?
That's the last half of chapter 5. Chapter 6 and chapter 7 is what the exam will cover. Last half of chapter 5, chapter 6, and chapter 7.
So the 3D rigid body, that's when we had the 6 equations,
6 equations of equilibrium.
and then we would flip the result. So if it's at a connecting point, and we say that CY is going this way.
Yeah, so the question is that where if we have a connecting point and we say CX, CY, we then flip it and say CX, CY, and no, this is actually frames and machines. So this is chapter 6, section 6.6. So the 3D rigid body is like I have a plate on the ground, right? I think you can. You have a plate on the ground that's supported at 3 points, right? That has a 700-pound load right here. Tell me what the force is at each of those 3 points. And so to do that, you have to sum of the forces in the X, Y, and Z, sum of the moments about the X, Y, and Z axes, and then solve. Okay? All right? So hold on. One last thing. I'll tell you here then. You're going to have a shear and moment diagram. Okay? There's at least one problem on that. You'll have one problem on 3D equilibrium. Equilibrium. Okay? You'll have one problem that's a truss, and you'll have one problem that's a frame or a machine. Remember that frames and machines, in order to solve this, you have to take it apart, and at the joints, you make sure that they go opposite directions. Okay? So there's your 4 problems for the exam.
Are we going to do 3-dimensional distributed loads in this class?
No, we're not going to do three-dimensional distributed loads in this class.
What class will we do that in?
I don't know.
Not in Mount Hood, apparently.
Not here.
Do you have to do that?
No, never. All right.
So if you go.
Yeah, so Miss Lee asked, am I going to specify a certain way on the truss, and I won't. You can solve the truss however you can solve it. It may be that you have to solve it one way, but I'm going to let you decide. All right?